Hey, so today we're going to talk a little bit about linear modeling, which is kind of the most common form of mathematical modeling because it's pretty basic. And so, as you can imagine, any kind of town planner or manager or anything, any kind of government office needs to make predictions in the future so that they can look at how many roads we need, what kind of schools we need, what kind of housing needs to be developed, all that kind of stuff. And so a lot of times they'll look at data like this where they are looking at population, right, that grows over time. So here's the population of Colorado and the data going from 1980 to 2010. And you can see that it is a fairly linear trend. Now, we are going to estimate it or approximate it by creating a line of best fit, right? And it's always a good idea whenever you're trying to make a line of best fit to go ahead and look at the data and think about, well, where along here is this line best going to predict what's happening? So if you follow this trend, right, I'm not necessarily connecting all the dots, although I did kind of manage to shutter and jank them all up. But you can see that your line should be spaced kind of in the middle where there's some on the bottom and some on the top. And it should be straight, which this one's not, but we do what we can. So that said, then once we visualize the line, then we're going to pick 2 points. Now, oftentimes those points will be at the end, but if you look, this point right here and this point right here create a really nice line that kind of goes through all the data, okay? Now, we want to be careful and really visualize the line because, for example, if we pick these 2 points, right, the line's going to be a little bit too steep, right? And that's not going to be very representative, okay? So let's look at this again. And I'm going to pick this point and this point. Okay. Now it's kind of hard to see the coordinates of the point, and so that's why I have included the data points here, right? So this is that first data point, this one, and this is the second to the last data point, which is this one. Okay. And I'm usually going to try and pick points that give me nice data. But so there are my 2 points. And I want to create a function p of x that models the population as a function of years. Okay, so the first thing I'm going to do is I'm going to find my slope. I might actually just type this out. I'll do my little insert equation thing. So m is going to equal what's that going to be? 4.7 minus 2.9 all over, and then 2005 minus 1980, which if I do all that math, that's going to be 1.8 divided by 25. Up here and see what that is, equals 1.8 divided by 25, so 0.072. Now, anytime you're using real world data, then we want to go ahead and use decimals, because that's what decimals were invented for. Anyway, so there's my slope. Now, I have a couple of points, and I can go ahead and write my equation in point slope form. And so I can say y minus 2.9, I'm going to use the first point, equals 0.072 parentheses x minus 1980. Now, what's nice about point slope form as opposed to slope intercept form is we can look at this graph and say, we can look at this equation and say in 1980, there were 2.9 million people in the state of Colorado. Now, one thing that I want to be want to be careful about is this says to you write an equation in P of X. So I'm going to change this just a little bit. And I'm going to insert another equation, and I'm going to say P of X P of X minus 2.9 equals Now, it's a little bit weird having this minus 2.9 there. So what I'm actually going to do is I'm just going to add that to both sides. So I'm going to get rid of it over here, and I end up with plus 2.9. Okay, I just moved it to the other side by adding it because it was subtraction over there. So now I have my function, which models the population growth in millions of people, right? So in other words, every year, 0.072 million people move to Colorado, or the population increases that by that much. And in 1980, there were 2.9 million people here in Colorado. So now I'm going to use my function to predict when the population was 2 million. So if I look at my units, right? So I've got on my y-axis, I have millions of people, and on my x-axis, I have years. So this matches up with my y-axis. So I'm just going to say, I'm going to insert another equation, and I'm going to say that P of X equals 2. Therefore, 2 equals 0.072 x minus 1980 plus 2.9. So now I'm going to need to solve this equation, right? And if I look at this, let me copy that. If I look at this, the first thing that I'm going to do, it's kind of go like that too. First thing I'm going to do is I'm going to subtract this 2.9 from both sides. So I'm going to get rid of that, put it over here, minus 2.9, and which 2 minus 2.9 is negative 0.9. And then I can divide it by this number. So let me copy that. Divide 0.9 by 0.72. Okay. That's going to get me 12.5. Negative 12.5. And then my last step is going to be to add 1980 to both sides. So if I add 1980 to both sides, then 1980 minus 12, so I'll add 1980. And I'm going to get 1967.5. So we can see that when P of X equals 2, in other words, when the population is 2 million, that occurred, according to our model, in 1967 and a half. So in like June of 1967, an excellent time. It's actually when I was born. But the important thing to note is that we looked at units and we plugged it in where the units matched in for P of X, and then we solved. Now, if we go down here, and we wanted to find out the population this year, which is not 2017, it's 2020, right? We can go up here and grab our equation. and plug it in here. And that unit matches up with my x coordinate. So I'm going to put in 2020 here and 2020 here. And then I can start simply evaluating. 2020 minus 1980 is 40. Let's copy that. Then 40 times 0.7, let's see what that is. Go back up to my calculator. Doesn't know what that means. 2.88. So let's go back here and say 2.88 plus 2.9 is going to be, let's gotta get rid of that. What's that going to be? 5.78 or roughly 5.8. Approximately, we can use our little approximately symbol. Approximately 5.8 million people, which if you follow this graph up, right, it's going to be come up here and like at 2010, and that's going to be just under, you can see that line extends up just under 6 million. Now, that's one of the things that I like about point slope formula is that this has real world meaning. These values in here, it has meaning in the problem. Anyway, but sometimes slope intercept works better. For example, here, like on the problems in the test or in the homework, right? You can actually see my y-intercept right there. I can be like, oh, look, my y-intercept is, I don't know, 28. That looks like a pretty good y-intercept if you imagine that line coming down. So we have that. And then we can pick another point like that. Now that's a pretty good estimate, right? And I don't need to faff around a lot and pick points that are, and pick points, I always pick grid points because they're easy to use. So for example, in this case, we're making an estimate, right? And we can only be so precise with that estimate, right? But so in this case, I can see that one of my coordinates is, I'm going to create some space here. Let's go back. All right. So here's my example from this one. Okay. So I can see 2 points here, right? One of them is this one here, which is 28 and 4. And the other one is 0 and 28. Now, what's nice about picking that point, because I can pick any point along this line, right? Why not pick something that makes it easy to work with? And in particular, save myself a lot of work by finding the y-intercept, okay? So now I just need to find my slope, okay? So I have these two things. I'm going to insert my equation here, and I'm going to say m equals, and then put in my little, this guy, and I'm going to say 28 minus 4 over 0 minus 28, order matters, right? Which equals 24. Well, I'll put my little fraction thing in there. 24 divided by negative 28, which is going to equal we'll call it 0.9. Because Alex in particular doesn't need anything very precise, right? And that's close enough. But it is negative, right? And we can look at this and we can see the graph is going down. It's a really good check. Now, we already know my y-intercept. So I'm going to say y equals my slope, negative 0.9, x plus my y-intercept right here, which is one of the points I picked, 28. And there's my equation. So let's go over here and I'll plug that in. Negative 0.9x plus 28. Now, at this point, so we've created this equation here, and then we're going to use our equation in part A to predict the time spent doing homework for a student who spends 18 hours watching TV. So 18 hours watching TV, that matches up with the units of our x. So we're just going to plug that in for x. So we're going to go over here. We'll copy our equation again. And we're going to plug in 18. Now, ideally, this would be in function notation, but they didn't ask for that. And so now I'm going to plug that into my equation. Or I'm going to plug that into my calculator. No, plus 28. So I'm just plugging 18 into my equation. And I get this value out, 11.8. And let's see where that fits. Yeah, that looks like that fits pretty well on that. That looks like that fits pretty well, right? Because 18 is going to be right here, which is going to be pretty much right there at 12. So that looks like that fits pretty well. So y equals 11.8. Cool. So now let me put that in here. And let's check. Yay! I got it right. Now remember, one thing I do want to point out is that if for some reason you got this, maybe you got it from help from a friend, or you're still feeling a little bit shaky, you can always hit the try another button. In particular, anytime we have a practice quiz, it's a really good idea because you'll see all of the different possibilities for that question. And then that'll really help you on the quiz. Anyway, I hope that was helpful, and I'll talk to you guys later.